consider it. But feel free to say whatever you want.
Just a remark that I try to do the same exercise Professor Miani gave to you. I found maybe closer result, nearly 0.2% of carbon. So maybe it can be linked to the difference. Maybe linked to the step of your computation, because it is sensitive. The criterion is certainly sensitive to this point. So I use a very small time step. Maybe Tayfun will give us information, but it's as it is derivative, the time step is very important here. So big time step may smooth the derivative. Sorry, it's a bit long because I have to link another computer.
Yeah, take your time. We are in a sort of relaxed discussion.
Yes. So when I try to use Pandat with the database, I saw that there was a possibility to directly plot the derivative. I don't know if you use this.
Yeah, the double slash. Yes, we are using it, but there is also some sort of discussion about that, because the point is that how can we rely on numerical derivation, which is one of the topics when Tayfun is very strong. And this is important not only in the solid fraction from 0.9 to 1, which is the range of solidification cracking, but it is very relevant as for grain size prediction, which is for the solid fraction that goes to 0, because after all, you are always working with derivative. So you are extrapolating in a way the behavior of the curve. There is a problem, generally speaking, using thermodynamics, that you have some problems in modeling the evolution of entropy, which is a little bit nasty because it has got to do with the derivative of logarithm terms. And the derivative of the logarithm goes to 1 on x when x goes to 0. And this is the point. But so it's interesting to discuss with it. I do not expect that we have any immediate results, but it is stimulating to have a discussion about the possibility, and so it broadens our knowledge and so on. This is not only an exercise, but it is in a more general framework, a discussion on the possibility of extending or not this methodology to some calculations. In my mind, for some alloys and from some specific welding, light alloys like you have been producing papers, Tayfun, it is interesting. About steels, there is this sort of there are quite a lot of open questions, chiefly because steels have a specialty. It's a complex field, but if we understand something about iron carbon for the moment, it would be nice. Federico, you can please turn on your microphone. You can say.
I don't want to disturb.
You are in discussion. You are not bothering anyone. So maybe I will switch off my own microphone. But it's a pleasure to have, because you are graduated engineers. You are already working in the industry. So a master, in my mind, an industrial-oriented master. This is sort of the quality of the master is not only the people teaching, but is the sort of the people working together. And this is the real quality of it. So you are not just listening to people speaking using slides, but you are interacting with them, which luckily we can do, and which is not that easy in the current situation. So Tayfun is in Turkey, Benjamin is in France, and we are in Italy, and we are open to discussion using some common language and common tools. Okay.
Fabio, I would like to say something. Actually, I have limited time because there's a meeting coming up.
Yeah,
and things are kind of rushing.
Yeah, and it's busy, but please.
Yeah, so there are a couple of different solidification models.
Mm-hmm.
One is sull,
Mm-hmm.
which assumes that there is no diffusion in solid,
Mm-hmm.
but complete diffusion in liquid.
Yeah.
And the other one is another extreme one, which is equilibrium.
Yeah.
It assumes that there is, there are actually both complete liquid diffusion and solid diffusion.
Yeah.
So Professor Ko used equilibrium solidification for carbon steel. But there is another one which is between these two solidification models. It's usually called partial diffusion.
Yeah.
Partial
You can do
diffusion.
with thermocast, but not with Pandat. I know.
Yeah, Pandat. I guess Pandat offers this in the 2020 or 2021. I don't know.
2021
version,
is not yet available, so we are up to 2020.
Okay. Well, I actually downloaded the demo version and it didn't work. Maybe they have the working capability in the full version, not the demo one. But so Thermocalc is able to do partial diffusion using the mobility data of all the elements. For example, you can set up carbon as a fast diffuser because it's really small, compared to iron atoms. Its atoms are very small. That's why it's kind of fast diffuser. You can actually use equilibrium for carbon, but it's not the only alloying element in steel. For example, you have manganese in it. Maybe you have chromium, you have nickel.
Well, we can. There is a solution even for Pandat. You should cheat the diffusion data and giving very low diffusion. Actually, they have low diffusion, but you can even cheat the Pandat. But the problem is that numerical. If you are doing some mess around, but we can discuss it with Van Zang, with some people of Computerm. But first of all, I believe there is no consideration in steel if you do not consider the iron-carbon system. It's like in aluminum alloys. If you don't consider silicon and sometimes copper, magnesium, then there's nothing. No? So the point is that how can we work out and how can we rely on this simple model? Because after all, in continuous casting, you have several classes. When you have a bloom caster, as long as I remember with my past life of a steelmaker, we had several classes of cooling. So you can divide, I think maybe the situation has changed because it was in the remote 90s that I worked there, and it was only up to 405 section round, which is a small bloom nowadays, but for the time it was the biggest. So we had some five ways of giving the water in the primary and the secondary cooling according basically to the carbon content. And so we share different classes. ABS, it was by that time casting some 1,000 of normal different steels, which NFA, as they say. And so the point is that we should try to work at first, working with carbon would be fine. And then we can also, I think, consider other issues, because the situation is preliminary. So this is a good point to start, because we can work in minutes with students this elaboration. If you go on other more complex solidification models, even in Pandat, then the simulations, they tend to go in the tens of minutes range. I don't know if some of you students have already done the simulation with other modules like the diffusion data. So it takes more time. But please, so how can we go on now? Please, I just shut one window because it's making some noise.
I put several things in slides, which are more or less what you said just now, Tayfun. So if you want, I can share this few slides. Inside, see that it's very close to what you said, and then I will show you maybe the new simulation if you want. So as Tayfun said, we have two extreme cases, lever rule, Gulliver Child, but I think you already saw this kind of thing. And the fact is that analytical relation to plot the evolution of the solid fraction. And the fact is, as Tayfun said, that yes, works. We have interstitial and substitutional atoms in steel. We have commutatory rules that said that more or less the radius need to be in the 15% with the solvent radius. So for iron, you see that manganese, molybdenum, chromium, nickel are in this range. And for interstitial solid solutions, the radius need to be lower than 59% of the radius solvent atom. So here we have nitrogen, carbon. I put also hydrogen just to show you how small it is. So these are necessary conditions, the size, but it's not only that. So for interstitial diffusion, I think it's pretty clear how it diffuse. The way that we have the diffusion, but for substitutional atom, you have also diffusion, but the main mechanism is in metals is linked to the vacancy diffusion. So in the crystals in the atoms. So I just put a table with diffusion coefficient at 1,500 degrees to show you the difference in terms of diffusion for substitutional. So at this temperature, we are really higher than carbon and nitrogen. So you see here, is 100 times more or less in terms of order of magnitude. It is really higher than the substitutional atom. So carbon is a fast diffuser, iron, and its back diffusion is particularly important in rapid solidification. So for example, for welding, but it can play also a role on casting. We are currently investigating this. So here we have. I just put a graph show you that this coefficient is following an Arrhenius law. So it is strongly dependent on temperature. So you can see here the level of temperature, and the liquid is here. Then you have ferrite, delta ferrite, and then austenite. So you see there is also a difference in terms of diffusion between ferrite and austenite. So a way to assess the influence is to work on the Fourier number. So this number is here. It involves the diffusion coefficient, the local solidification time, which is linked to the cooling rate, and a characteristic size, which is often taken as half the secondary downstream arm spacing, which is represented here. So I won't detail this because it's an analytical relation, but what you have to keep in mind is that the Fourier number depends on the cooling rate, and increasing the cooling rate is equivalent to decreasing the TF here. So for very high cooling rate, the Fourier number is going to 0, and we have the Gulliver-Scheil relationship. And the Fourier number goes to 0.5. We are at the equilibrium curve. You see here, just as an illustration, the effect of the cooling rate. We are going from equilibrium to be closer to Gulliver-Scheil relationship. Just finally, I have just a plot to show you that I did equilibrium with Pandat and the database Professor Miani gave us, and also Gulliver-Scheil with this the same database. And I tried to compare it with a software we are using in Metz in ACM, which is GMAT Pro, where we have the possibility to include a fast diffusion of carbon, and you see that it is in between. So just to show you that in this case, if you try to plot the criterion, the cracking criterion, the slope at the very high value of the solid fraction. So in this case, I used a log scale because there is a really different scales in this case. So the equilibrium is here. Here you have the Scheil with fast diffusion of carbon, and the upper curve is the Gulliver-Scheil. So you see that the order, the magnitude are really different if you are using this different approach. So there is a strong influence of the hypothesis that you do on the criterion value. So I think it is consistent with what you just said, Tayfun. I don't know if you have comment or question on that.
Good. Yes, I have a comment that everything is interesting and it is very stimulating for the discussion. Thank you, Benjamin. And I believe that for continuous casting, in my mind, a very quick indication could be done by simple using equilibrium data. This is my feeling for the moment, but maybe I'm wrong, and I'm open to discussion. Of course, I like it because it's already ready to use. This is maybe,
yes,
but of course, I believe that the time scales are in favor, at least of for using of carbon. But I am up to discussion because I'm just a participant to discussion. Not I am the professor and you are the nonsense. Okay. But it is impressive in any case that these differences give, and it's also interesting because you have some motivations for the. Normally, the students, if they have to study diffusion, they don't like it. Yes, they know this fixed law and so on.
Interesting.
Nothing serious, nothing to deal with us. But then I know by person Hervé Combeau. I've been attending many years ago, unfortunately, it's a solidification course in Switzerland,
Yes.
in Lezione. It was, I think, 2006 or 2007. So I'm an old man, and but yes, it's important to stress. And also, I was lecturing on solidification processing using, unfortunately, this also many years ago, using the Fredrickson course, which is materials processing during casting. It is a very good text, some mixture of practical things and some practical, but too many years ago, nearly 10 years ago. And so I believe that the whole issue could be studied, but the true response could be given by plant production data, because you, and then this we will discuss maybe in, not now, because you have the plant data and you have some ideas what's going on on steel. You've been casting so many heats that you have some impression what can be applied. So I believe using different models and testing them against the responses could be also interesting. This is in any case interesting because this is your own calculation.
Yes, on the right-hand side, yes. I used Pandat and your database with a batch, so it was really fast. And I have to admit, I'm sorry that I used the criterion computed in the software for this. So
yes, it's okay.
With a really low temperature step. So I assume it is not so bad, and when I compare to the result of the paper, I think that it's really close. In this case, so it's equilibrium, yes. And what we see, just to have a comment on what you said in the casting condition. What we often see is that medium carbon steel are not that easy to cast. Big section, and here we see that it seems not to be so difficult with them if we just see the curve, and in reality it's not that simple. So that's why I think there is at least things that can be done here, because we have to keep in mind that in this case we are mainly austenitic during the solidification, and in the diffusion I put the plot here, so you see that the coefficient, the diffusion coefficient for austenite, which is here, it is really at least one, but more than one order of magnitude lower than ferrite, and so it can play a role on the final part of the curve, and this is particularly important for this criterion.
Tayfun, any remark? Federico, any remark on that?
Yeah, I agree with Benjamin. If you deal with steels, you gotta deal with diffusion, because you have different alloying elements with different sizes. Interstitial diffusion, substitutional diffusion. If you are just dealing with substitutional diffusion, then shale would work fine. But if you have both, then you need to consider different diffusion mechanisms. or if you have just carbon in iron, well, equilibrium could give relatively better results, but even iron atoms kind of diffuse into the other iron atoms. So there is also diffusion in iron atoms in iron. So this also affects the the shape of the solidification curve. That's why to be able to get accurate solidification curves, you gotta deal with diffusion.
And maybe you have the same remarks for medium carbon in welding.
Yeah, I think so. The paper co-published doesn't consider diffusion. If it was considered, then probably there would be some changes on that medium carbon. You're right. I mean, I don't have much experience with casting of carbon steels, but I totally understand you. You have the experience. You don't see good results when you cast medium carbon. So yeah, I understand your doubt about the calculation, and that's actually showing the missing part of the calculation. They don't include diffusion, but there is diffusion actually need to be considered while calculating. So yeah, I agree with you. Things can potentially change. Fabio, I would like to ask you to give me a permission to leave, because
you can leave. We can talk after, but it was nice to have you. Yes, so we are from 3 countries, quite far one another. So it was nice to have you, and also to have your lecture before. And so we will keep in touch, and we will develop our discussions maybe by email. So enjoy your day and have a nice day. Thank you for being there.
You too, guys. Yeah, I would love to enjoy the rest of the presentation, but
it's okay. It's just a discussion, so yeah, we can go on. Okay, ciao. Okay. Have a nice day.
Thank you.
Bye.
Thanks, Benjamin, for the great presentation. See you.
Thank you.
Okay. So I think it is in any case stimulating. I believe that for teaching purposes, I mean, Pandat is fantastic, because you can introduce people on this problem on solidification, cracking, or real examples that you can work out. And then you can also introduce the diffusion. And we will see, because I believe in 1 month we will have the new edition of Pandat. And as long as Pandat, they tend to mimic the thermocalc, I think they will try to propose. Federico, would you like to add something to our discussion? I would be pleased.
No, personally, I need to go deep in the technical papers, but I would like to understand which is the correspondence with the real experiment data, what we see in the simulations. I don't know which is the extent as of now, the comparison.
I think we should have some time to have this answer.
Yes,
but you can give your feeling, maybe, Benjamin, which is correct. So your feeling is totally disagreeing, something agreeing, some yes, we could have or.
As you said previously, I think it's a work in progress. Let's say that the first element we have is that it gives interesting trends, but we have to take into account back diffusion. If I think this curve that is computed in the paper and we worked on with Pandat is not clearly in line with what we see on hot tearing in a continuous casting. So I think it's a basis, but we have to deal with back diffusion if we want to go further and see if if this kind of simple criterion can be helpful for continuous casting. So it's a work in progress, but it's yes, it's a state of now, let's say.
So let us assume, Benjamin, that you can work out by means of MATLAB, Octave, what else. I think I have already done it actually, but for the students of the other course. So let's say that you can have solidification curves, and then you have the content of the element, not only carbon. Then you can have an answer, modeling by means of response surfaces, which is basically multiple linear regression. Then you have a basic tool. Then you can have some ideas, because what about if we introduce, how about using a little bit more of molybdenum or titanium or what else in our steel? This could be very interesting because you have answers in terms of minutes. And then, yes, you can then try to go on. And of course, as long as we have very simple tools, it would be impossible to have the truth. But maybe we can compare the trends and see what's going on with that. And I think it is, you can prepare some batch files, and then you can run with some basic, and it is also why I insist on the thermodynamic data, because the thermodynamic data nowadays, it's some 30 years that people is working on it. You have open data which are reliable. I mean, you can use them with some sort of feeling that you reproduce at least the phase diagrams without troubles. And so you have the equilibrium properties quite good. So you don't have to buy from an external provider, which can provide anything to you, and then you don't know what it is inside that. Because if you have a commercial database, do not forget that the commercial database is encrypted. So you don't have any idea of what it is, the complexity, or maybe you can have some, of course, you can decrypt, reverse engineer or what else, but then it's, but having things open, it's a common, maybe baseline to have a discussion. And then, which is my idea, if companies want to go on, then maybe ACM or any other, they must produce their own open, I mean, but open internally database to work out. And this could be done at least for elements, taking into account what we have not discussed with the student, which is important, the grain refiners. And the grain refiners are sort of titanium, vanadium, niobium, and all other elements that are relevant to the solidification. And even using such simple models, for instance, in the solidification of light alloys, solidification of copper alloys, you get the difference. If you use in those alloys, you basically use aluminum, titanium, boron, which is ALTIB, they call it, and it is you really see the difference from the experiment and from the modeling. And I believe steels are much more complex because it's some 10 or even 20 elements that are linked together in special steels. So you never know if there is the effect of nitrogen or what, or some, but it is a good baseline. And it is not so resource consuming. So it is lean in a way. It is simple, and it is much more than having just a phase diagram in your hands. Something more. This is my impression, Benjamin. So it will not solve the whole issue, but it could give some suggestions.
I fully agree, and I would say that it is important to work on the material composition on the one hand and on the process on the other hand. And sometimes you have problem maybe during casting or whatever the process, and you don't know if it's process, if it's a problem of process or a problem maybe of the material. And here we are looking at really the solidification of the material based on its composition. And whatever the process, we are looking at how the element are influencing the solidification curve, and so we can be more sensitive to the composition itself and see how it has a consequence on the solidification. And so we have to work on the alloy composition and also on the process, and maybe they are a complementary tool. It exists a complementary tool, and this quite fast criterion can be helpful to deal with really the material itself and the solidification property material. So I think it is yes, it could be an interesting tool if we are able to check that it provide at least good trends in terms of cracking susceptibility. So
okay. Any bonjour, comment ça va? The connection is working, so this is important because when you are using Teams, then it goes and everything goes, but sometimes it doesn't go at all. So it's good to have you here, and welcome to our discussion. We were more on technical issues in the continuous casting, but we can welcome you for a while, and then we can. Okay, so you should. Why don't you turn also the microphone? So we can hear from you and check that you can speak. Yeah. Turn on the microphone.
Okay.
The microphone.
Now.
Yeah. Perfect.
You hear me? Yeah.
Bonjour.
So I will not stay until. And I want to. I have a meeting before that. I just wanted to.
Yeah, this is important because with a colleague, professor, we took 20 minutes from the professor of Oxford to reconnect by Teams. So it's fine that you have this. I'm very pleased to see you and to hear you well before the official start of the lecture. Thank you so much for taking the time.
Take care.
Okay. See you later.
Great. Bye.
Wow. Okay. It was important for me to check because otherwise we lose time. I will also try to upload the presentation of Dr. Vira if I find because he just sent me to me. The only point with the discussion that I have to deal with different messages when I am online with some meetings at times it's a little bit complicated because I have to follow the discussion and then to answer to the people that's interested to join or not the discussion. So, but Benjamin, my idea is that I am telling, I will work with some students, I don't know, we will work and develop some ideas which actually should be the final work of our course, not necessarily all working on this topic, but so we can try to see maybe for plain carbon steels, then we can add something more about, I would say, very basic elements and see what's going on. And then we can submit, because this is the activity for the course. And it's very nice to have a real world. And the real world is always more complex than exercises for students. And so a master is like that. It's something that you are working towards finding a solution. The good thing in a master that you don't have your boss that, yeah, why haven't you done it? So we are here open to solve problems and pleased to solve problems, but if we don't solve the problems, it's we keep our position without too much problems. One point that I'm strongly discussing with my students of the other mechanical engineers, that they want me to have me in person in the next week. They want to have me in the classroom, but in the classroom we cannot use Pandas because we don't have the laboratories. So 60 students, I'm begging them to work from home in remote, and they don't want. They want to stay in the classroom with the mask and blah, 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 without using computers. So, and having someone that will speak, pressing the presentation. I think it's some the old man, that's me. They try to do new things that, and how could you deal with you are in Metz, I think, I don't know where Dr. Bira, I think it is in the zone, so it's in France, but in another place. And the other guys is from Turkey, and we are in Italy. And if we move and make a meeting, it takes traveling, money, and time, and it's fine to have this sort. And I am pleased to have this sort. And I'm quite satisfied. I hope that the students also are satisfied by the sort of international interaction that we have in this course, because otherwise hosting people from abroad, it's a mess, and it's expensive, it's time consuming, because when you have them in Udine, you must go tour around and blah, blah. It's very nice sometimes, but sometimes it takes really some weeks. When I had Sadoway from MIT, it was very nice having him in person, but it was a little bit complicated. Okay, any suggestion, Benjamin, for any homework to do, we can do for you? What would you like us to explore from the situation?
You have to. We are limited to 3 elements, no? With a demo.
Yes, we are limited, but I am not limited, because this is the problem that I have the 218. I have all the databases, professional databases, which are not. I do not tell the guys from Panda. The professional databases are not that different from the open databases that I made, because I've been checking it and it's not too bad. But so I have professional databases, so we can do whatever the composition would be. We can try, as was the original idea, some kinds of deals. I will find 5, 6 kinds of, and see how the situation is going on. Real world deals. Yes. We started this task, but doing with some people is much better, especially for calculations, because if you, Benjamin, have some results, and the results are as the paper, as Federico or Emanuele or whoever have the same, we can rely on the calculation. So it's very nice that using different ways of approaching. So you are using which kind of temperature step in the solidification simulation? Or you have, so this is an important issue. I think it's important to underline it. But if using different values, we obtain the same results, we are not that bad in using the algorithms.
Yes, I have to check, but I think...
Because the lie that you are producing, that some of the guys that have already sent me in the previous week, I valori, speaking in Italian, but you understand, yes, a little bit. I valori dei calcoli della derivata seconda coincidono più o meno con il paper per chi ce lavora sopra, vero?
Sì, circa, a meno di un piccolo errore, poi variabile a seconda della singola curva, però sì.
Tollerabile, no? Tollerabile, assolutamente. Ragazzi, va benissimo Federico, ma se qualcuno di voi vuol dire qualche cosa di più o fare una domanda o dire potremmo concentrarci, io guarda sto proprio lavorando su uno strano acciaio che mi chiede il cliente. Okay, so if you have any suggestion about, or even in the makes of the, so ABS steel is making basically some carbon steels because they are also now enjoy the carbon steels business for some reasons, especially for wire. But then basically they have special steels which are basically alloyed with nickel, chromium, and molybdenum. Then any other element of the periodic table, but mostly nickel, chromium, and molybdenum.
Yes, chromium, molybdenum, and maybe 20 Mn4 or 15 Mn4, for example, to increase the type of alloying element.
You can suggest. We are basically around 12 persons here. You can give us our own works. Try to propose, I would say, 10 compositions, because if you make the batch file, I would suggest that in the batch file you use just database.tdb, and then I will substitute with PAN 2000. I will substitute the information in the batch file, and I can run it on my PC, and then it takes more time because I have installed in a portable PC which has not a very good processor, so it takes a little bit more time. I think using good computers it's good sometimes, but you don't have to use monster computers, but to use properly Panda, but it helps.
The temperature step was 0.1 that I used. But I can share the batch file because I used it.
Yeah, you can if you want, but you can send it only to me because I want the students
yes, yes.
to create the files. So they must do that. But it's good. I think that you know, using these batch files and blah 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 blah, it's nice that we can I mean, consider metallurgical problems very close to reality. Maybe not a professional way, because if you want to go professionally, you must spend a little bit more money than for free. But it's a good starting point. Okay. Any other thing to say? Then we will leave you. You will send me by some compositions that you want to try, and then they will make the batch files, and we will run them basically on my PC, and we will see the results. Or even we can approximate the compositions, because I don't believe if you have 0.3 of manganese or 0.20 or 0.25 of silicon, that it doesn't change much on the solidification. So we can assume that at least for some kinds of steels, you can use, and if you have to use alloying elements, it goes more important for other, but we can try to model simple solidification. We will discuss the issue, and we will propose you something about that. Okay?
Yeah, I have six grades that are more or less ready. I can send it to you.
Yeah.
In fact, it's 5 because the 6th one is really close to another one, so it's 5. And here you will use equilibrium in this configuration with contact. So I send it to you.
Yeah.
And,
got it. Okay, thank you. And also the chemical compositions. This we can share immediately. And the batch file, no, no, not yet at least. Okay, the chemical compositions. Here, and then okay. So basically, it's there on the chat, and it's 6 grades of. So it is 15 manganese 4, 10 chromium molybdenum 8, 10 chromium molybdenum 4, 440 chromium molybdenum. Yeah, basically it's chromium molybdenum or manganese compositions.
Yes,
yeah,
simple ones.
That's good. Okay.
If you want more more complex with more alloying, I can find one also. I think.
No.
But
I don't know. We can start. We can start with that. Let's see what's going.
Yes,
what's going on.
It's interesting, I think, because it's very classic one.
Okay. Okay, for the moment, Benjamin, I think if you will have the time at least to read our emails or to rejoin us, and because it would be nice to so which is my impression. Tayfun is strongly for using diffusion data. It's okay, but as long as I don't have any other possibility, I would go with thermodynamic at first, because this is what I have in my hands for the moment, and then I can explore other opportunities or other, but I want to be sure that using thermodynamic is useful or not. And this I am not sure. There are some pros, some cons. And yes, there is also this problem of using sull. Then you don't have the possibility in Panda to have this split use. But in any case, even using sull, if you use real diffusion data that I have, the physics will do it by itself. So the physics will allow the carbon atoms diffuse, and the other substitutional elements do not diffuse. And so it's not any impossible problem.
You are able to do that in Pandat with the actual release of Pandat?
I can use solidification model, the old solidification model, but I cannot use the more recent 2020 or 2020 direct simulation of. But I don't think it is so important. We will see. So I will use just basic algorithms, and then I will build them on the basis of the calculation that we will use. Okay. For the moment, it's all with you, Benjamin. I think if you don't have to have any question from you guys, or any specific interest in what they are doing in SEM. In
if
Metz.
you want, I prepared just few images to show you what it looks like numerical simulation.
Yeah, it would be fine if possible.
I can show you because it was a question. So if you see the screen, it's a bit messy, but
no problem. My way as well.
But I wasn't prepared to do this, so I didn't clean up the desktop. So here you can see what we do most of the time is to compute the evolution of casting. So here we are dealing with primary cooling. So we have the steel, and you can see here the solid fraction. So the software is Tercast, which is provided by Transvalor. So you can see that there is assumption in this calculation. So, for example, we are not modeling the submerged entry nozzle here. We assume that the matter enters at the meniscus as an homogeneous flow, which is a strong assumption because we are not looking in this case at the flux in the mold, but we are more looking at the evolution of temperature and thickness of the solid skin. And then you can do such calculation, obtain a slice, for example, and put the slice in the wall machine to see the evolution of the solidification. It's heavy, so it takes time. Doesn't take so much time usually, but on this well, while it is loading, let's say, I can just show you that we are also able, we are looking also at flux in the mold. So we can, for example, model the SEN and see the evolution of the fluid flow in the mold. You see here the evolution of turbulent flow, let's say, at the close to the submerged tree nozzle in the casted product. We can also use this kind of simulation to assess the very recent feature in the software, but we are also looking at how inclusions are going in the molten steel flow. So we can we can put in the simulation inclusions with a given diameter and a given mass density, and see how it goes in the flow. See if it is well blocked, let's say, at this step, or if it is stick in the solid. So that's something we are doing. I don't know what happens now. It's always like that when you want to show something. But well, let's we will show you. I can show you a rolling simulation, which is done with another software, which is called Forge, which is a cousin of Tercas, let's say, because it's also provided by the Transvalor. And here you have a numerical simulation of rolling. So here we have the rolls. And here it is a bit particular because it is a steady state simulation. It means that we have an initial state, and we compute until finding the steady state solution of the rolling of this bar, and then we can look at results like, of course, temperature, distribution. So you take into account the cooling due to the contact in this area. You can see the strain levels you have in the rolling pass. You can also try to look at damage criterion. That can be interesting for surface defects or and so on. So you can with such tools study the process, try to help people from the production to optimize the tools, the geometry really of the roll. To limit, for example, this kind of damage criterion, and that's something we can. That's something we are doing with our colleagues in Udine. So of course you can look at pressure and so on. So if you see the mesh here of the problem, in fact, to be able to limit the time consumption of this simulation, we use a quarter of the geometry. We use a symmetry plan, so we just compute on this part, and then we are able to see the whole results. Okay, I don't know if you have remark, question on that. You see here what it looked like, numerical simulation. So this kind of simulation is quite fast. In fact, for one pass like this, it takes it's the magnitude is in hours of computation, so it can be 1 hour or a little bit more, but it's really it's really fast. Let's say if we compare to a numerical simulation on Tercast. So for casting simulation, so here you have the whole machine. With rolls, with sprays, you see the sprays and so on. So if I just show you maybe, well, I've been a bit far, but for example here, if we look at the temperature field, you will see the influence of the sprays, I think. See here that you take into account the cooling due to the rolls and also to the sprays. We can maybe plot cooling rate. Maybe it could be no, it's not maybe like that. It could be easier to see. No, it's not. Well, but what you have to see is that we take into account the evolution of the temperature on the surface of the big bloom. So here it's a casting of 600 millimeters bloom, and we are able to compare with real in situ measurements that are done with pyrometer, for example, on the production site, and we are able to check the values and validate the numerical simulation in terms of evolution of the temperature on the surface, and so we are able to be more confident in the numerical simulation also in this case. I didn't mention it, but we are able also to model the carbon segregation and the segregation, the macro segregation that can be occurring during the continuous casting. We do it also on ingot, and it is very interesting, but we need a lot of material parameter. So we have to be able to model the macro segregation. We have first to be quite accurate in terms of micro segregation at very low scales, let's say, and then we have also to be able to model accurately the flow. So Darcy law and the material parameter linked to the, for example, Darcy law in the mushy zone. So it involves also the downstream spacing, for example. So there is several aspects at the material scale to be able to model the macro segregation at the level of the product. So that's something we are looking at, but it's still difficult to be always accurate with that. But we have some good results, for example, on ingots. So I won't present it, but I don't know if I have maybe images. yes, you have that liquid fraction here in an ingot, and you can see the flow, the convection in the molten steel here. So you see, and with this kind of simulation, we can also look at macro segregation and compare it with experimental data that are obtained on real ingot. So that's it. If you have any remarks or question, please feel free.
Hi, Benjamin. It's Gabriele Guastaferro speaking here from Danieli Research and Development Center. And I'm part of the office that treats and studies the continuous casting. And we work a lot on the CFD of continuous casting machines, starting from the tan dish, arriving at the molds. Personally, I've never studied solidification by means of CFD, but I have some question about it. We perform usually some calculation about the SCN characterization, monitoring, for example, the meniscus velocities, and sometimes the inclusion fate inside the mold. And the question I want to ask to you is, how do you characterize the solidification? I mean, the CFD software can give you lots of information about cooling rates and temperature and flow fields inside the mold. But as you told before, it needs a very deep characterization of the material, right? So inside the software, you have to consider how all the solidification curves, all the liquidus curves, for example, on diagram, modify depending on the cooling rate, for example. So you need to insert all this kind of information. Is a very huge amount of parameter to consider, right?
Yes, you're right. It is exact. In fact, I didn't mention it, but just a remark that for now, our software, the software we used, in this case, Tercast, is still not able to model electromagnetic steering, which is really important on the flow in the mold. So that's why we didn't focus a lot on fluid flow in the mold, because we lack one of the main parameter for this. So I just tried several simulations to see if we were able to do it and prepare the next step, which is including the electromagnetic steering, because it is announced in the next release of Tercast. So we will be able hopefully to do such computation with EMS in the coming months or years. I hope it is months. But you're right in terms of material parameter. In fact, it is a software dedicated to solidification. So in this case, it's not really a CFD software, only CFD. It is based. It is focused on the modeling of solidification. So I would say it is the opposite. It's solidification, and we add CFD software in the molten steel. Let's say so. We need. You're right. We need a lot of material parameter, and again, when we need a lot of material parameter, we can use CalFAD to do that. In fact, we use the CalFAD software to generate the material file. and it includes a lot of material parameter. The solidification curve, but also the evolution of the flow stress. For example, we are able to determine the flow stress depending on what are the phases in our solid phase, so the answer is that yes, we have let's say a small database which is provided by the software itself with the software. But if you want to go deeper and deal with other steel, we have to develop our own material file, and we use CalFAD software to do so. So for us, it is GMAT Pro, but Thermocalc or other softwares like that can generate this kind of material files that we use in this software.
Okay.
Yeah, even you could even use, in my mind, you could use the basic ideas by Miettinen, I never know which is the right, is a man from Finland, a colleague, and he has developed over the year the IDS. I don't know if Daniele is still using IDS or not. It was a model for solidification in continuous casting. But the idea is to use CalFAD and then to make calculation about the phases. Is not very difficult. You can even implement, once you have the CalFAD data, you can even implement by any kind of, by Excel, by MATLAB, Octave, or whatever. I believe, I don't know, if we will have time, we will use it to model some copper alloys and some iron alloys as well. I don't know if we will have the time over it, but it is nice because you can have, all the basic information, for instance, thermal conductivity or what else. So some that are related empirically, actually, to the phase. So which is the picture in metallurgy? The phases, yes, you can predict if you are lucky enough not to have very big diffusion problems or very big segregation problem, which is another story, but you can have some ideas, but sometimes you need to have some data on the, let's say if I want, because this is one of the things I want to do, you want to do high aluminum steels. I'm trying to arrange some experimental casting with some friends in the industry locally, and but if you want to have physical data of 10% aluminum steel, what you should do? Yeah, that's a problem.
We are out of
not
the
1%, but 10%.
Our software, we are out of the range, I think.
Yeah, totally. And so this is the problem, basically speaking, with all the commercial softwares, because if you want to do one step beyond with the compositions, you should, please, yes, provide me a new database or a new model, and then you must pay money. Normally, it's not for free. And you don't have, this is my position. So in the long run, using something, not necessarily everything open. For instance, a company which is a competitor but of Daniele, but is not, they are making electromagnetic steerers, which is Ergolines, which is based in Trieste. They are using OpenFOAM for doing the simulation for the electromagnetic interactions. And I think they have been using it, I think, in the last 10 or 15 years, and they have quite good results. In any case, we should try to compare the new future trends of Tercast with those. Maybe we can make some sort of arrangement. I don't know how strong the competition is. I think Ergolines now is a company as for steerers. Of course, there is Rotelec, which is in France as well, but they have done some nice work over the years, and I think they are providing some steerers even to ABS. So they are competitors, but not totally out of the door. Like some other real competitors of Daniele, bigger than Ergolines, which is a company around 15 guys after all. And thank you for the discussion, and thank you, Gabriele, for the interactions. And if some of you have some more details, it's less like an official presentation, but it is I believe, even more interesting, because we can try to develop ideas, interactions, and also it's also good to improve the communication between the University of Udine, which is local, but then you are the research center of ABS Acciai, and then you are the research center of Danieli, and so on. So we are trying to increase the communication. This could be useful, not necessarily not today, but maybe in the future. Of course, you have also other links, professional links. I think you are connected as ICM already with some guys in Danieli Research Center or in Danieli, generally speaking. So for the moment, are there any questions for the other guys for the any specific? They have a lot of useful instruments in ACM. They have simulation tools. They have also some physical tools to make. For instance, they have the possibility to do hardenability testing. I think you have a quench dilatometer, which is
yes,
not so common to have in.
Quenching dilatometer, and it is equipped with a deformation module.
Mm-hmm.
So in fact, we are trying more and more to use it as an experimental simulation of, for example, rolling process to study the recrystallization during the rolling process. So we can apply one or two or more deformation step and see how it the mechanical response evolves, and because it is basically a quenching dilatometer, we are able to quench the specimen and look at using metallography the grain size and so on to study really the material response to external loads at high temperature. We have also a scanning electron microscope here in Metz. We have classical mechanical machines to perform, for example, hot tensile test up to more than 1,000 degrees. Of course, it is able to perform tensile test at room temperature as well. We have fatigue tests. We have also machining equipment for machining our samples, for example. Yes, we are just a bit more than 20, but we have interesting equipment here. We have also ultrasonic testing. It is more focused on production, but it is an interesting tool to study the internal soundness of product and check that our products are good enough for our customers. So yes, we have several interesting things. We can do classical analysis like hardness. We have also an optical emission spectroscopy to study the chemical composition of steels, for example. We have combustion apparatus to study carbon and sulfur. So yes, we have interesting things here.
Yes. All the toys, but something some are common also to other, but some you are appunto this special equipment like the dilatometer, which is not that common, and also some mechanical tests, as you mentioned, is something rather unique. It's not always possible to have all the toys in one place unless you are a very big, I don't know, but even in the big R&Ds, you don't have all the toys. I was speaking about a friend of mine who yesterday visited the Pometon. Pometon is a company manufacturing metal powder, so they have a lot of toys. Actually, they have got X-ray diffraction, which is rather unusual for an industrial company. Normally we have it, I've been using it in the university. And sometimes you are a little bit over-equipped because you need like these people that Dr. Marco Peloi that met us in a discussion a couple of weeks ago. Their problem in my mind is to make an industrial use of these very sophisticated technologies like the synchrotron radiation and so on, which is from the physics, from the basic physics, and from the big investment. It's some 400 people working there, I think, in synchrotron at Trieste, which is like, I think in Grenoble is even more, where you have the synchrotron radiation facility in France. And sometimes it's useful to make these technologies available. I wouldn't say for quality testing because it would be too expensive, but to test for some experimental work, maybe to get some EU funding. Okay?
Yes, you're right. I will one day finish the presentation I spoke with you a few weeks ago, because in this presentation I present more in details the recrystallization study using the branching dilatometer.
Yeah.
And
we will be pleased to have it for sure.
If, I will finish it and I will show it to you. And the second part on the presentation is on a PhD we are that just finished with ACM, which is focused on pore closure. And in fact, yes, we used several experiments from the dilatometer experiments, the plastodilatometer. We say plastodilatometer when we use the module, the deformation module, to a bigger lab scale experiment, forging, which is a representative forging test. The representative is to say that we are trying to be representative of the mechanical loading we have in the rolling mill of ABS. And we used a specimen with a calibrated pore that have been done with foundry. So we have a calibrated pore in our samples and we forge it. And after that, we followed it using microtomography. But it was not in ESRF in Grenoble or in Trieste. It was with let's say lab apparatus of X-ray tomography, and we can see the evolution of the pore closure at different level of deformation, and that useful tool to also to validate the numerical simulation. So to be more confident in it, and then when we are confident, we can use numerical simulation to look at the evolution of shrinkage pore, for example, during rolling or forging process. So that's something we are also looking. Currently, is to try to apply numerical simulation to follow the pore closure, and hopefully tomorrow it will also be interesting to study the shrinkage cavity healing. When it is closed, it's one thing, but for internal soundness we need perfect healing of the defect. So that's something we are working on.
Okay.
So maybe one of the next event I will show you
for sure.
Slides about that.
Yeah. For the moment, I think it's if there are any other question from the guys, Valeria Daneluzzi or Terence Nobile, or or we have Simone Ferrarese, or we have Nicola Minussi, and so on. And I think Giovanna Busolin. Any of you that would like to have, do you have any doubt about what you have done on the iron carbon cinder cool paper simulation that you want to ask or to propose to all of us? Or maybe we can just stop for a while, because then we will have to listen to the presentation of the Dr. Bira. You say Bira? Yes, in France.
Bira.
In France, because I have to say properly okay. So I think for the moment it's very interesting, very nice, because it's something that we can work on. Because my idea is for this specific course that we have some small, a few pages, I would say, papers based on the results, what it is possible to achieve or not by using this methodology. As long as I'm focusing in these months to using these very simple CALFAD models for modeling of the solidification in broad sense, in welding, in continuous casting, in component casting using low pressure die casting, or even so I am interested in develop in a single issue of open paper journal this approach, because I believe this information is in one place and in the other. It's difficult to have everything in one place, and especially about the potential of the methodology, which is, in my mind, quite good. So we will see if it is applicable in this important field of continuous casting of steel. Thank you, Benjamin, for your time here. I don't know if some of you, because everyone is busy, because then I have some mails from other guys, and it's always a problem to fit all the things from the. So we will stop a while, and then we will meet again with the students in around 11 o'clock. So you can leave if you want your computer and your screen, maybe have a coffee or what else. Thank you, Benjamin. Always pleased to be in touch with you, really. Okay, have a nice day.
Thank you. You too.
All the best. Ragazzi, io torno verso le 11, qualche cosa del genere. Prendetevi un caffè, rilassatevi un secondo. Ok? So we will relax.
Va bene.
Va bene?
Grazie.
A più tardi, anche perché poi dobbiamo sentire la presentazione di Birà, che non vi ho ancora caricato. Allora. Carica dal computer locale, giusto così sappiamo che cosa andate. È una cosa di sostenibilità, quindi un po' diversa da esigenze di tipo tecnico, però la sostenibilità, il green steel, che cosa, Birà è il padre, perché è quello che ha creato questa serie di argomenti che oggi come oggi nelle tematiche di questo European Green Deal, direi, ci stanno tutte, secondo me. Non a caso Birà è stato il capo della parte ambiente di tutta l'ArcelorMittal, adesso non lo è più perché è in pensione da un po' di anni, però secondo me è interessante ascoltarlo. Certamente non entrerà nelle tematiche di tipo quantitativo, però secondo me è comunque interessante, perché poi dà il trend. Lui andrà a sponsorizzare un po' la conferenza che fa, è una persona comunque attiva da tanti anni. Ci sono delle note su questa chiacchierata che abbiamo fatto, soprattutto col Benjamin. Avete da dirmi qualche cosa? No, vi lascio il caffè, dai, fatevi una pausa caffè, quello che volete. Ci vediamo per le 11.